Welcome to the Explainer. So, let's talk about one of the biggest challenges in the entire software world, complexity. How do you manage it? Today, we're going to dive into how these massive, modern applications are built to be solid, scalable, and actually maintainable. And we're going to use the core principles of Java as our guide.
So, here's the big question, right? You've got millions, sometimes literally millions, of lines of code. How on earth do you keep that from collapsing into just total chaos? A complete mess. How do the pros build software that can actually grow and adapt over time without breaking everything?
Well, the answer, in a word, is architecture. And for this explainer, I want you to put on a new hat. You're not just a coder, you're a software architect. Your job is to design and build a whole, sprawling digital city from the ground up. And all those concepts in Java? Well, those are your tools. They're your blueprints, your zoning laws, the whole shebang.
Okay, so here's our game plan for building this city. We'll start with the Architect's Challenge, then we'll jump right into Blueprints for Code, that's inheritance. After that, we'll talk about one action taking many forms, then we'll cover zoning laws and city districts, the universal power grid, and finally we'll wrap up with some of Java's other really smart tools. Let's get building.
All right, first up, Blueprints for Code, or what we call inheritance. Look, any great architect will tell you you do not start from scratch for every single building. That's just crazy. You use proven designs, you build on what already works. In the world of Java, this powerful idea is called inheritance, and it is all about code reusability.
So here's the core idea. Inheritance is a mechanism where a new class, let's call it a child class, just automatically gets all the properties and behaviors of an existing parent class. What does that mean for you? It means you only have to write the code for what's new or different. I mean, think about that. It saves a ton of time and cuts down on so many potential errors.
And here we see the simplest version of this in action. This is called single inheritance. You've got your main blueprint, right? That's class A. Then you create a new, more specialized blueprint, class B, that builds right on top of A. So B gets everything that A has, plus whatever new stuff you decide to add to it. This is like the fundamental building block of our entire city.
But of course, it gets way cooler than that. We can take that basic idea and really run with it. On the left, you've got what's called multi-level inheritance. See how the blueprints are just stacked in a chain? C is built on B, which is built on A. It's kind of like adding floors to a skyscraper. Then on the right, you've got hierarchical inheritance. Here, one single base plan, A, is used to spin off a whole bunch of different specialized buildings, like B, C, and D. This is how you get all that rich variety in your city, all while starting from one solid foundation.
Okay, so we've got our blueprints, we've got our buildings, but now how do they actually do stuff? This brings us to our next big idea, one action, many forms, or as the pros call it, polymorphism.
Polymorphism, it literally just means many forms, and it's this awesome principle that lets the same action have totally different outcomes depending on the object. Think about it like this. You tell every vehicle in your city to move. What happens? Well, a car is going to drive on the road. A boat's going to sail on the water. A helicopter? It's going to fly. The command is the same, move, but how they do it is completely different. And as you can see, this idea splits into two main flavors.
So let's break down these two flavors. On the left, you have compile time or static polymorphism. This is all figured out before your code even starts running. It's like having a button that's physically hardwired to a light. You press it, the light turns on. It's super fast, very predictable. Now, on the right, we've got runtime, or dynamic polymorphism. This is the really flexible one. The decision about what happens is made while the program is running. It's more like a universal remote. You press the power button, but what turns on depends on what you're pointing it at. That dynamic flexibility is just incredibly powerful for building complex systems.
All right, so we've got blueprints for our buildings, and we've got rules for how they behave. What's the next logical step? We need to organize the city itself. Because let's be honest, a city without organization is just chaos. So now we're talking about zoning laws and city districts, or in Java terms, packages and access modifiers.
So what's a package? Honestly, the best way to think about it is as a neighborhood in our city. It's just a way to group related stuff together. You know how a real city has its financial district, its residential areas, an industrial park? Well, a big software application does the exact same thing. You'll have packages for the user interface, for all the database stuff, for the core business logic. It's all about keeping things neat, preventing chaos, and making sure you can actually find what you're looking for.
And this table right here, this is basically our city's zoning code. These are the access modifiers, and they set the rules of the road. So public is like a main highway. Anybody can use it, from anywhere in the city. Then you have protected. Think of that like a private road inside a gated community. The residents and their close family can use it, but not the general public. And private? Well, that's what goes on inside your own locked house. No one from the outside can see or touch it. These rules are absolutely crucial for keeping your city secure and stable.
Okay, our city is taking shape. It's organized. But now for the big question. How do we get all these different parts, these districts, these buildings to actually work together? We need something like a universal power grid, a standard way for everything to connect. And in Java, that's where interfaces come in.
An interface is, at its heart, a contract. It's a set of rules. It says, hey, if you want to plug into our city's power grid, you must have this standard three-pronged plug. The grid doesn't care if you're a tiny lamp or a giant factory. All it cares about is that you follow the contract and have the right plug. This guarantees that anything that implements the interface can connect to the system in a totally standard and predictable way.
So why do we even need this? Why is this so critical? Well, here's the thing. In Java, a class can only inherit from one parent. It can only have one direct blueprint. If you tried, like you see here, to have class C inherit from both A and B, things would get messy fast. If A and B both have a build method, which one should C use? It's a classic conflict, sometimes called the diamond problem, and it's a huge headache for architects.
But what if there was another way? With interfaces, it can.
And here is the elegant solution. A class can't inherit from two parents, that's true, but it can sign multiple contracts. It can implement multiple interfaces. So, a single class could promise to act like a vehicle and promise to act like a data source, for example. It just has to follow the rules for both contracts. This lets you mix and match capabilities from all over the place without any of the confusion or conflict. It is the ultimate tool for flexible, modern design.
Okay, we've hit the big pillars of our city's architecture. Now let's do a quick lightning round, a tour of some other super smart tools that every good Java architect has in their toolbox.
First up, the static keyword. So what does this do? Well, a static thing doesn't belong to any one building or object. It belongs to the entire city. The perfect analogy is a public clock tower. There's only one of them, right? And anyone in the city can look at it to see the time. It's a shared, central resource.
Next, we've got varargs. It's short for variable length arguments, and it's a super handy little tool. It basically lets a method accept a flexible number of inputs. Think of it like a delivery service that's ready for anything. It doesn't matter if you have one package to send or 20, it can handle it.
And finally, we have to talk about maybe one of the most important unsung heroes of our city, garbage collection. You can think of this as an automatic cleanup crew. It's constantly working in the background, looking for abandoned buildings, objects that are no longer being used, and it clears them away to free up valuable land or, in this case, memory. The best part? It's all automatic. It keeps your city clean and efficient without you having to lift a finger.
So let's bring it all home. The big takeaway here is that these things we've been talking about, inheritance, polymorphism, packages, interfaces, they aren't just a bunch of random Java keywords you have to memorize. No way. They are fundamental principles of design. They are the tools that allow us as architects to take on massive complexity and build something orderly, robust, scalable, to build software cities that are truly built to last.
And that brings me to my final question for you. These incredible ideas, reusable blueprints, universal contracts, organized districts, they're not just for code, are they? Think about it. Where else do you see these same principles at work? Maybe in business or even in nature. It's something to chew on.